In this lecture, I will talk about capacitor and inductor. First, let's see what is a capacitor. A capacitor is a device that stores electrical energy in a form of electric field, so it can store energy. And it is like a passive electronic component with two terminals. It has two terminals, and it is a passive component, and it stores electrical electrical energy in the form of electrical field. Okay, how we can build a capacitor? A capacitor is made up of two metallic plates with a dielectric material in between the plates. So first, the definition of the capacitor, we can say a capacitor is a device that stores electrical energy in an electric field. Okay, I said that it's a passive element with two terminals. Here is a schematic of a capacitor. It consists of two metallic plates. So let's have two metallic plates. Okay. With a dielectric material between the plates. So let's say this red color is dielectric material between these two plates. Okay. These two plates are connected to as the terminals to the other parts of the circuit. So let's say terminal A and terminal B. But how does it work? We know that when we apply a voltage over the two plates, so if we apply a voltage over these two plates, an electrical field is created. The electrical field is created between these two plates. I'm showing these electrical fields with red arrows, and these electrical fields are between these two plates. Positive charge will collect on one plate, so one plate will have positive charge, and negative charge on the other plate. So other plate will have negative charge. Now, if we disconnect the capacitor from the circuit, the capacitor stores positive and negative charge between these two plates in the form of electrical field. Okay, we have some parameters for this capacitor. First of all, as I mentioned, these two plates are are made from conductive materials. So there are metal plates. Between these two plates are filled with dielectric material, which could be glass, air, vacuum, plastic, or any dielectric material. And there is a distance between these two plates, which we call it D. Each plate has a surface area, which we call it A, and each dielectric material has a parameter called dielectric permittivity. We show it with epsilon. So each time dielectric permittivity. We show it with epsilon. Okay, so these are the parameters we have. We have epsilon, which is dielectric permittivity. We have D, which is distance between two plates, and we have A, which is the surface area of each plate. So before doing some calculations and equations, let's see how we show a capacitor in the circuit. The symbol of capacitor is like this. So here we have a symbol of the capacitor. So capacitor has a current going through it, which we call it with I sub C of T. There is a voltage across two plates, which we show it with VC of T. Okay, what is the amount of the energy that can be stored by a capacitor? We call this energy capacitance of the capacitor. So the capacitance of a capacitor determines the amount of energy that can be stored in a capacitor. And the capacitance of a capacitor is equal to capacitance is equal to epsilon A over D. So it shows that by using dielectric materials with higher permittivity, we can have stronger capacitors, or by increasing the surface area or decreasing the distance between the plates, we can achieve more capacitance. The unit for capacitance is farad. Farad, and we show it with F. Now, what is the relationship between current and voltage in a capacitor? Because for all passive elements, even for active elements, we always looking for the relationship between the current and voltage in a circuit. In a capacitor, the current of a capacitor is derivative of the voltage. So we can say IC of T is equal to C dVCT over dt. Of course, the C here is the capacitance of the capacitor. V is the voltage across each two plates, and I is the current. So current in a capacitor is derivative of the voltage. If we integral both sides of these equations, we will have integral of dVCT is equal to 1 over C integral of ICT dt. If we rearrange this equation, we will have integral of dVCT from VCT0 to VCT is equal to 1 over C integral of T0 to T IC x dx, and which gives us this relationship. VC of T is equal to VC of T0 plus 1 over C integral of IC x dx. So this equation says that the voltage across each capacitor is the integral of the current. And of course, we will have an initial conditions, which is equal to initial voltage, which was on the capacitor. So in summary, I said that the IV current voltage relationship is that the current is derivative of the voltage, and the voltage is the integral of the current. What about the energy? The energy of capacitor can be found using this equation. Energy of capacitor. WC of T is equal to 1/2 of C voltage square. So in order to find the energy of a capacitor, we need to have the capacitance and the voltage across the capacitor. The capacitor absorbs power from the circuit when storing energy. So when storing, to absorb power when storing energy, and deliver the power or return the power when delivering energy. Delivering energy. Okay, so what is the power of a capacitor? The power of the capacitor. In order to find the power of capacitor, we need to multiply current by the voltage. So P of T is equal to I of T times V of T, which is equal to, instead of IC of T, we use the derivative equation. So we say it's equal to C dVc of T over dt times Vc of T. If we calculate this, simplify this equation, we will have power of capacitor is equal to derivative of half of CV squared. Okay, here is the equation for the power of the capacitor. So we learned what's the power of capacitor, what's the energy of the capacitor, what is the voltage current relationship in a capacitor. Now here we want to talk about the equivalent capacitance. What if we connect more than one capacitor in series or parallel? What is the equivalent capacitor? We know that for resistors, we can simply find the equivalent resistance by considering two rules. First, if for resistors, if resistors are in series, we just add the resistances, and if the resistors are in parallel, we add the conductance of the resistors. But what about the capacitors? Let's assume we have n capacitors connected in parallel. So here we have C1, C2, up to Cn. So if we have n capacitors connected in parallel, despite the resistors, we can simply say that the equivalent capacitance is equal to the total of the capacitances. So we can say C equivalent is equal to C1 plus C2 plus Cn. So for parallel capacitors, we can use this equation. Okay. What about the series capacitors? If we have n capacitors connected in series like this, C1, C2 up to Cn, we can say 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over Cn. So for series capacitors, we can use this equation to find the equivalent capacitance. Okay, let's do some examples. Here is an example. It says a following figure shows voltage across a 0.5 microfarad capacitor. Find capacitor's power. Okay, so here is the figure. So we will have x-axis and y-axis. X-axis is time in milliseconds, and y-axis is the voltage of the capacitor in volt. And we have 1, 2, 3. In vertical axis, we have 5, 10. Okay. And yeah. Okay. So this going curve is the voltage of this capacitor. So we have three lines, which we need to find the equation for those lines first. So let's see what are the equations. The equation for this line, of course, is Vc of t is equal to 5t. The equation of this line is Vc of t is equal to negative 5t plus 2, and the equation of this line is just 5. Vc of t is equal to 5. Okay, now that we have this information, let's solve the problem. We know that current I C of t, current is equal to, let me just write it down. IC of t is equal to C dvct over dt. Okay, so from t from 0 to 2, IC of t is equal to 0.5 d over dt of 5t, which is equal to 2.5 milliamp. So this one is the current for t from 0 to 2. For t from 2 to 3, IC of t is equal to 0.5 micro d over dt of negative 5t plus 20. So in the figure, the equation of the second line is negative 5t plus 20, not 2. Okay, 5t, negative 5t plus 20, which is equal to negative 2.5 milliamp. For the third region, which is t greater than 3, IC of t is equal to 0.5 micro times d over dt of 5, because 5 is a constant number, constant value, the derivative is equal to 0. So we got to this point. Let's draw the current characteristic. So here is the current curve. IC of t, here is t, time 1, 2, 3 milliseconds, and we have 2.5. The current is in milliamp, and we have negative 2.5. And if we draw the curve, we will have a horizontal line from 0 to 2 with the amplitude of 2.5, and a horizontal line between 2 and 3 with the amplitude of negative 3, and 0 for the rest of the plot. So we got the current figure from the voltage. Now it's time to find the power. Of course, we know that power is equal to current multiplied by voltage. If we multiply current and voltage for t greater than 0, less than 2, the power will be equal to 2.5 times 5t, which is equal to 12.5 t milliwatt. For t greater than 2, less than 3, the power is equal to negative 2.5 times negative 5t plus 20, which is equal to 12.5 t minus 50 milliwatts. And finally, for time greater than 3, power is equal to 0 times 5, which is equal to 0. Okay, so we got the power for all time. Now let's plot the power. So in order to plot the power, or sketch the power, in order to sketch the power, we again have this time in the form of millisecond and the power in milliwatts. And for vertical axis, we have 25, we have negative 12.5, and we have negative 25, T1, T2, T3. For 0 to 2, we have straight line. We have this signal from 2 to 3. We will have this P. This one is the value of P. And for the rest of the regions, we have 0. So here is 0 and 0. And okay. Okay, that's the result. And if you look to this figure for the power, we see that it has two regions, positive and negative. So from 0 to 2, the power is positive. From 2 to 3, the power is negative. So from 0 to 2, we can say that the capacitor is absorbing power, absorbing power, and from 2 to 3, it's delivering power. Okay, so now that we learned about the capacitor, we will use the capacitor as well as resistor in our circuit. The next element which we are going to discuss in this lecture is called inductor. Okay, inductor is a passive electronic component like resistor and capacitor, which is capable of storing electrical energy in the form of a magnetic field. Magnetic field. So the difference between capacitor and inductor is that the capacitor stores energy in the form of electric field, but inductor stores energy in the form of magnetic energy. And it's basically, it consists of a wire that is wound into a coil. So we have a coil. Here we have a coil and a wire that is wound into a coil. So here is a wire, okay, which we wound around the coil. And this is a basic structure of an inductor. So when the electricity flows into a coil from left to right in this direction, this will generate a magnetic field inside this coil. Okay, so this one is the basic definition of inductor. It is a wire, conductive wire, which is wound into a coil. And in the circuit, we show inductor with this symbol. This is the symbol of inductor. It has two terminals, terminal A and terminal B. Okay, again, like resistor, again, like capacitor, inductor also has some parameters. It has the current moving through the inductor, which we call it IL of t. There is a voltage across two terminals, which we call it VL of t. And of course, inductor has something called inductance, like capacitance for capacitor, resistance for resistor. We have inductance for inductor. So inductance is represented in Henry. So inductance is represented in Henry, and we show it with capital H. Okay, so this one is a general form of an inductor. And again, like capacitor, let's see what are the IV relationship between, what's the IV relationship in inductor. So IV relationship. Okay, if you remember, for capacitor, I said that the current is derivative of the voltage, and opposite of the capacitor in inductor, voltage is the derivative of the current. So in an inductor, we can say V sub L of T is equal to L DIL of T over dt. So here is the main equation. The voltage is derivative of the current, and of course, the current will be the integral of the voltage. So we can say IL of T is equal to IL of T0, which is initial conditions, plus 1 over L integral of T0 to T VL x dx. So this one is the current as a function of voltage in an inductor. Okay, what about the energy? Energy in inductor can be found by this equation. W of L of T is equal to 1 over 2 L IL squared. Okay, so we have the energy of an inductor, and the power of inductor is shown in this equation. P L of T is equal to IL of T times VL of T, which is equal to D over dt 1 over 2 L IL of T squared. Okay, and this one is the power of an inductor. The power can be positive or negative in the inductor. What about the equivalent inductance, like what we saw in resistor and capacitor? For inductors, we have equivalent inductance. Let's see. Let's assume we have N inductors connected in series. Okay, and it is L1, L2 up to Ln. For series inductors, we can say L equivalent is equal to L1 plus L2 plus Ln. It is opposite of capacitor, but exactly same as the resistors. Okay, so in order to combining several inductors, the inductors act exactly like capacitors. Now if we have n inductors connected in parallel like this, so we have L1, L2 up to Ln, we can say parallel inductor or inductance, in fact, not inductor, parallel inductance. Let me fix it. Inductance, parallel inductance is equal to 1 over L equivalent is equal to 1 over L1 plus 1 over L2 up to 1 over Ln. It is exactly same as parallel resistors. Okay, let's see one example for inductors. Example, find the equivalent, not just for inductor. Let's see an example for capacitor and inductor. We want to find the equivalent circuit. Find the equivalent circuit. Okay, so here is the circuit, the connections. We have one inductor here, another here, connected in parallel. There is a capacitor here. There is another capacitor here. Two more capacitors here. And we have one more inductor here. And that's it. So we the values for this element are 700 microhenry, 700 microhenry, 300 microhenry, 1000 microhenry, 0.05 microfarad, 0.02 microfarad, 0.1 microfarad, and again 0.5 microfarad. Okay, so let's solve it. The two inductors here are in parallel. So in order to find the equivalent, we multiply them and divide it by the total. So it is 700 times 300 over 1000. It's equal to 210 microhenries. And these two capacitors are in parallel. So the equivalent is simply the total of these capacitances. So 0.5 plus 0.1, which is 0.6. And then we can say 0.6 microfarad is in series with 0.2 microfarad. So it gives this value 1 over 0.2 plus 1 over 0.6 to the power of -1, which is equal to 0.15 microfarad. And we will have this circuit. Okay, the values, of course, are 210 microhenry, 0.2 microfarad, and 1000 microhenry. And then we can say that these two inductors are in series. We cannot combine inductor and capacitance. So it's like orange, apple. So we cannot combine orange and apple. Okay, so we can combine inductors by inductors and capacitors by capacitors, resistors by resistors. Okay, so here is the reason why I'm not like consider this capacitor as a series with those two inductors. So if we simplify this circuit, we will have one capacitor and one inductor, the values of 1210 microhenry and 0.2 microfarad. And here is the final answer. So our original circuit with 1, 2, 3, 4, 5, 6, 7 elements is converted to a circuit with two elements, one resistor and one inductor. Okay, so this was like introduction and introducing capacitor and inductor. We continue in the next lecture.